Welcome back to hypothesis testing with normal distribution. This is part 2. So we're going to go and have a look at question 2 now. And just as we saw with binomial distributions in year 1, we can take a different approach to hypothesis testing where we find a critical region. So in question 2, part A, we've got this null hypothesis, alternative hypothesis. Here's the sample size and here's sigma. So let's write out our distribution. So we're going to say that x is normal with mean 70 and variance 1.2 squared, or standard deviation 1.2. X bar is normal with mean 70 and variance 1.2 squared over 30, and let's also find its standard deviation. SD is 1.2 over root 30, which is 0.219. I'll leave you to check that on the calculator if you want to. Now, this is a one-tailed test. So what we're going to do is we're going to use the inverse normal. We're going to find area 0.05. So what we're really saying is if we sketch out a distribution like this, we want to find this value here, so that this probability is 0.05. And then if we had a test statistic, we would say, does that test statistic lie in that critical region? So we're going to say inverse normal area is 5%, 0.05 as a decimal. So let's go and have a look at that on the calculator. So on the calculator, we're going to go into the inverse normal. So we're going to go 3, and we want area is 0.05. We want sigma is 0.219. Actually, you can put that in here as 1.2 divided by root, what's it, 30. So you can see that's 0.219, and we've got a mean of 70. Enter, and here we get a value of 69.64. So gives 69.64. So our critical region is, critical region is x bar is less than 69.64. Okay, let's look at B. So B, we've also got a one-tailed test, but this time it's the other way. So we're going to say x is normal with mean 1000, and what's our standard deviation is 1. So our variance is 1. Then we're going to say x bar is normal, mean 1000, and variance is sigma squared over n, so 1 over 100 over 100. So standard deviation is the square root of that, which is 1 over 10, or 0.1. it's one-tailed, so we want the inverse normal. Our area is, in this case, is not 1% because we're going the other end. So we've got this. We want this to be 1%. So area equals 0.99. We're always finding areas to the left there. So gives, and again, let's put this in on the calculator. So we want area 0.99. We want standard deviation 0.1, and we want mean 1000, and that gives a value of 1000.23. 1000.23. So critical region is x bar is greater than 1000.23. So if we get a test statistic which gives us a value of greater than 1000.23, we're going to say that we're going to accept the alternative hypothesis. So have a look at C now. So C, we've got x bar is normal, mean 25, and standard deviation root 10, so variance 10. Sorry, this is x. I'm putting x bar there. X bar is normal with mean 25 and variance 10 over 250. So that means standard deviation is the square root of that 10 over 250 is 1 over 25, so equals 0.2. It's two-tailed, so we're going to say 0.005 each tail. So we want areas 0.005 and 0.995. And those give the values. Well, let's go and look them up again. So we've got we've got 0.05. Standard deviation is 0.2, and the mean was 25, and that gives us 24.485. 24.485 is that. And let's also go and look at if we change the area to 0.995, and that's going to go 25.545. So it should be 485. I think I've written all the thing down. 485 at 25.515. So the critical region is, critical region is x bar is less than 24.485, or, and we could write that as union, x bar is greater than 25.515. In other words, if we get from our sample that a mean which is less than 24.485 or greater than 25.515, we're going to conclude that the population mean there is significant evidence that the population mean is different from 25. I'm going to pause there and then come back for the question 3. Okay, for question 3, we've now got a full hypothesis test. I'm not going to read through the question, so you might like to pause the video and do that yourself. Let's go into it now. So, for part A, we're going to write out the distribution. X is normal with mean 65 and standard deviation 12, so we've got 12 squared here. So this is the national distribution that's given in the question. National distribution. N equals 30, so X bar is normal, put that in there, with mean 65 and variance 12 squared over 30. So our standard deviation for this SD is 2.19. So that's 12 over root 30. You can check that value. We want to state our hypotheses. So H0 is mu equals 65. H1 is mu is greater than 65. Greater than 65 because the maths teacher's belief is that her students outperform students throughout the country. Significance level is 0.05. So probability that X bar is greater than 70, which is the test statistic that we've got here, is, well, let's go and calculate it. There we are. So we're going to put in one, we need normal cumulative distribution, which is 2. We've got a lower value of 70 now. Upper value of something large, let's put in 1,000. Standard deviation of 2.19 and a mean of 65. Let's return that and we get 0.0112. 0.0112. 0.0112 is less than 0.05. Less than 0.05. So the test is significant. Except H1, and we're going to say there is sufficient evidence that the teacher's class outperforms the rest of the country. There we go. So for part B, we're going to say that it's exactly the same test, but with a significance level of 0.01, and we would say probability that X bar is greater than 70 equals 0.0112, which would be greater than 0.01. So the not significant, and we would reject H1. Okay, so change the significance level. So the significance level is going to have a strong bearing on whether the test succeeds or fails. In part C, what's different is that we've now got a two-tailed test. Using your calculation, state whether her head teacher's belief that students' results differ from those nationally at the 3% level. So now two-tailed, in other words, H1 is mu is not equal to 65. Significance level is 1.5% each tail, are 0.112 is less than 0.015. So again, the test is significant. In other words, we would accept H1, and then we would write some context to say that the head teacher's belief that the students' results differ from those nationally there is sufficient evidence that. Okay, so that's the end of this video on hypothesis testing with normal distribution. It does take a bit of practice, so very strongly advise you to go and do as many questions as you possibly can on this.